All right, everyone, we're going to go ahead and get started. We've got the last few people coming in, so if you can find your seats, if you are here, that's great. Hello, everybody. Thank you so much for being here at our Science on Tap. We are really excited about today's topic, and I'm just thrilled that you are all here. My name is Cinnamon Moffett. I'm the Research Program Manager here at Oregon State University's Hatfield Marine Science Center, located in Newport, Oregon, which sounds a little weird if you're in the room. I already did it. That was meant to keep us all in the box. And that's because this is a hybrid event. And so that means we have just as many people online as we do typically in the room. So for folks that are online, thanks so much for being here with us. This is a webinar. So that means that your cameras, mics, and screen shares are disabled. But Roseanne is our volunteer. Hi, Roseanne. Roseanne is going to help us navigate the chat. So if you have any technical issues, you can't hear, you can't see, or if somebody lowers the mic like that and you can't hear them anymore, please let us know, and we can give feedback to today's speakers in the chat box. Also, at the end of today's talk, because this is a hybrid event, you can put your questions into the chat box. Roseanne will read them out for our presenters today. For folks in the room, when we get to the question and answer, you will need a mic. And so all you need to do is raise your hand and we will run around and make sure you have a mic so that folks online can hear the question as well. Okay, so I wanted to just make a couple of really quick announcements. Next month, Science on Tap has not been scheduled yet. Thank you very much. And that will be Steve Rumrell, who works with ODF&W's Shellfish program. So he's going to come and talk about several of the research projects that ODF&W is working on. Stay tuned. We'll try to get you that information soon. If you are not getting emails from me and you are curious about our seminar events, there's a sign-up sheet over here on the side of the auditorium. You're welcome to sign up there. The only thing you'll get are events like this. And you won't get a bunch of spam from me, I promise. But we do hold all sorts of public events that you'd be welcome to come to. So just letting you know that. The other thing that I was handed, which really everyone should know about, and if you don't, we have Marine Science Day coming up next month on Saturday the 13th. This is a huge open house for us where all of our researchers come out and they have tabletop exhibits and allow us to explore and play. So I'm hoping that you all have an opportunity to come. It is a free event that runs from 10 to 4 on the 13th. So if you have questions about this or you're curious or you'd like to hang a poster at the place where you shop or play, we have some extra posters over there. But the reason you're all here tonight is for today's speakers, and they have conveniently put together welcome slides that introduce themselves. So I'm off the hook and I'm going to hand this off and allow them to introduce themselves. But again, thank you all for being here.
Thanks, Cinnamon. So welcome, everyone. The introduction slides are in a couple slides. So our talk tonight is how does glacier ice melt? So hopefully we give you a taste of that, and then how we're making measurements at this face of this very scary and actively calving glacier. So this is our team from last summer, standing on the bow of the Steadfast. And you'll see a few photos of this research ship. We were up at the face of this glacier for about 10 to 12 days or so last summer. And there's different universities involved. Oregon State's not the only one. And we've had this research supported by a few different foundations. So my name's Meagan Wengrove. I'm an assistant professor here at Oregon State University. And my background has mainly been in sediment transport and morphologic change of coastal areas, turbulence and boundary layers. And that is the piece of the puzzle that I'm bringing to this very collaborative team.
Hi there. I'm Jonathan Nash. I'm a professor at Oregon State University. My background is physics, and I started in more oceanography and plain old oceanography, trying to understand how heat gets transported through the ocean in places like the Gulf of Mexico, where the surface water temperature really strongly affects things like the hurricane strength and whatever. And so we work in places like that. But what we're going to talk to you today about is, the ice-ocean interface. And I love exploring the dynamics of this really crazy boundary layer, the interface between the ocean and the ice, using lots of interesting technologies, autonomous boats, and teams of undergraduate engineers and even retired engineers who help us build, crazy things to sample the physics of the ice-ocean boundary.
Hi, everyone. I'm Erin Pettit, and I'm a professor in College of Earth, Ocean, and Atmospheric Sciences here at Oregon State University. My background is in geophysics, and my specialty is ice. And I basically like ice in almost all of its forms. My favorite form is glacier ice. And I've worked all around Antarctica, in Alaska, in Greenland, up here in the Cascades, really trying to understand how glaciers interact with both the atmosphere and the ocean. And these are just a few photos from some of the different landscapes and tools that I use. We think about how water flows through and over and in these systems. And all the way down to the picture, the colorful picture in the middle is actually a slice of ice if you look at it through polarizing lenses. So just take two of your polarizing sunglasses and put a piece of ice between them, and you will get a version of this. This is in the laboratory with some special, with a just more precise cutting. But ice is incredibly beautiful, and it's also it's a very funky part of our system. And so what we wanted to do was come together as looking at where the ice meets the ocean, and especially what happens at those boundaries. And so this collaboration kind of came to really kind of intensely look at what happens at the boundaries of the ice in the ocean, which is a bit like what's here on the right there. That's from a glacier in Alaska. And so just to get us started on all on the same page, ice is a really critical piece of our global system. The cryosphere is a relatively new term. It happened after I finished my PhD. I think we came up with this term, the cryosphere, in regular use. But this is because ice happens at both poles. It also happens in a lot of high mountains everywhere. And you'd be surprised at how many countries you don't think would have ice around the world, how many places, even at the equator, that have ice that's part of their system. The one key thing towards our conversation today is that there's a very big difference in terms of how sea ice, which is frozen ocean in the Arctic, behaves compared to how glacier ice, which is ice created from compacted snow that falls from the sky, forms. And so this picture shows us sea ice. On the right, you see sea ice over the Arctic Ocean, and then Greenland is one of our largest areas of glacier ice. And the next picture that I'm going to show will also provide a little bit of an understanding of how glacier ice interacts with these systems. So the snow falls, covers Greenland. The Greenland ice there is about 2 miles thick. So we have 2 miles thick in the center of Greenland, and the colors here show how that ice flows from the center, where it's 2 miles thick, out to the edges where it falls into the ocean. And it's just that gravitational downward flow from the thicker ice going to thinner ice that drives that flow. But what happens is that it all gets funneled through these fairly narrow valleys, and it tumbles right into the ocean, which is a big clue as to why that this boundary where the ice moves into the ocean is has some of the biggest gaps in our understanding of the global climate system, and where our global climate might go in the future. And what has been found over the last decade or so is that Greenland has been retreating. We have mass loss everywhere. The Antarctic ice sheet is losing mass. All of the glaciers in Alaska are losing mass. All of our glaciers here in the mountains up through the Cascades of Washington and British Columbia are all losing mass almost exclusively. And if you have questions about any that aren't, come ask me afterwards, and I'll help you understand why there might be a few glaciers here and there that are actually advancing. But the critical thing is that this boundary where the ice meets the ocean is a really sensitive place and changes there can have impacts upstream and change the glaciers on a much larger scale. And in particular, what we really zoomed in on and are going to talk about today is that it's the melting of the ice underneath the ocean, so in the ocean, that is much more than we used to think was happening, or it's more than we thought than our current models were predicting. That ends up triggering some of the retreat in ways that we hadn't expected. And the reason, there's just to provide a little bit more detail. So this is just a close-up example of a glacier from the bottom in this case, because I'm sitting in a helicopter taking this picture. This is in Antarctica, by the way. But the ice is flowing down and then it hits the water there. And at that water, we have two things happening. We have calving, so the big icebergs coming off, and then we actually have melting. And for many, many years, we mostly focused on calving. Like, what's calving going on? How much calving is happening? But it turns out the melting, directly melting into the ocean, is just as important, or more in some cases, than the calving. And that's what has driven a lot of our work here. So before I pass it off back to the oceanographer, this is a time-lapse image of LeConte Glacier, which is, or Seidel Zit, which is the proper name for it. And this is a time-lapse image that really just hopefully emphasizes to you this idea that this glacier is flowing at about 20 meters per day of ice flows into the ocean. So it's a lot of ice that just tumbles into the ocean, either by calving or by melt. And I am going to pass it off.
Okay. Yeah. Thanks, Erin, for a nice introduction. So when you looked at the previous picture that Erin showed, was this, this glacier, which has so much motion in it. And you might think that the glacier is just controlling the show, but we sort of have this argument back and forth. And I keep saying, no, it's the ocean that's controlling the show. And this gives you a little bit of an idea. The red shows you the vectors of velocity, or the speed of that water. But you can see, again, this is a time lapse over, I don't know, a single day, I guess. And there's just a tremendous amount of motion in the ocean. And these waters are very warm. And so depending on how those warm waters melt the face of the glacier, one of the hypotheses is that warm water can control the speed of the glaciers upstream. And so that's sort of why we are doing this. And if we take this and just come back and look at a side view of what is going on. So the previous picture showed you the surface structure and how those surface currents were all swirling around. In addition to that, there is this general circulation whereby the glacier on the left is melting, and melting waters from a glacier are fresh water. The ocean is salty water. So what happens when you have fresh water and you put fresh water into salty water? Does anybody know? What do we got? Did somebody say it floats? It melts. Okay, so it melts, yes. But if we have a cup of fresh water and a cup of salty water, does anybody know which one is heavier? Salt water. Okay, good. So if you put a cup of fresh water at the base of this glacier and you released it, what happens is it rises all the way up to the surface. Okay. Now, by the time it gets to the surface, it's actually not fresh anymore. It's almost all salty. And that's because it's mixed with all that fresh water, that salty water that was in the fjord, and it has brought a lot of that water up. So for every cup of melting fresh water, by the time it gets to the surface, it's like 35 cups or 100 cups of salty fresh water, which means it has brought in a huge amount of ocean water to mix with and rise it up to the surface. Why this is important is because of that heat arrow. The ocean waters are actually really warm. And as the North Atlantic waters for Greenland are warming, we think that those warming waters are being brought more quickly towards the glacier face and causing enhanced melt. And so it's a circulation pattern where the ice melt is driving this upward flow of fresh water along the face of the glacier, and that is drawing in these warm waters from the open ocean and further enhancing melt. And so these are the sort of the concerns we have, and we're trying to understand what are the processes that are happening near the glacier face. And we're trying to do that in more and more detail. I'll tell you a little bit more about this instrument, but this is the type of instrument that we are using. And we are trying to bolt an instrument like this to the face of a glacier like that. Now, this gives you a little bit of a perspective on what the water looks like near a glacier face. And, you know, it might look kind of flat and calm, but if you then advance the slide, here's a little kayak that we built, and you can see how fast it is driving just to stay still against these meltwaters, which are boiling up at the face of the glacier. And this guy is actually deploying a mooring. You can see it dropped something off the back, and it's going to drop a big chain and anchor, and that instrument is going to go fall to the bottom of the fjord. It's gone. And it will sit there for a couple of weeks to make measurements. So this was sort of the first types of things we did with these autonomous boats to make measurements near the face of glaciers to understand what's going on. What we were trying to do was understand why Alaskan glaciers are melting 100 times faster than the models seem to be predicting. And so we went there one year and we measured these melt rates, and we're like, oh my gosh, they're melting so much faster. What's going on? What's going on? What's going on? We wrote a paper. So we've been trying to figure out what's going on. And Megan's going to talk right now because Megan has something to say.
Yeah, so this set of pictures shows, I mean, if you can think about controlling this robotic boat, you can see it in the little tiny boat right in front of that big splash. That's what we're doing, is looking at this boat through binoculars and being like, oh shit, you know, it's a big one. That's a really big one. So I would say I've done like 10 years or so of field work, and this is by far the most stressful field work that I have done. Just where no one's in that boat, by the way. No one is there. The reason why we're doing these robotic measurements is because it would be obviously unsafe to put a person in that boat. So we're not putting people there. These are all operated remotely. So how do we make these measurements? Well, we need a bunch of new tech to do it, right? We can't just depend on things that we've used in the past. And so one set of platforms that we've used are these robotic boats. They're called Aries and Polly. Jonathan's been working on these in his lab for the last decade, maybe, in some form. And we've kind of taken his streamlined boats and put all these crazy things off the side, and we'll explain some of those as we go. So we've used a bunch of different platforms. And we'll go into depth on each of these a little bit more. So we've used these ROVs that have the melt stake on it. So the ROV is remotely operated vehicle, 2 different types. We've also used drones. Erin's going to tell us about that. And we've used the multi-beam sonar to map the underside, underwater of the ice, hanging off the side of the boat. And we're going to go into depth a little bit more. But before we do, this is kind of the chaos that we had on the Steadfast, trying to put all these things together and make sure they work and put them in the water. And then when they don't work, you know, soldering on the ship and putting them back in the water. So we spent, 2 weeks kind of going back and forth between this tiny space. And there's about 16 different scientists and engineers on the boat. And then the crew is another 5 people. So it's a fun and crowded atmosphere. Okay, so melt stake.
Okay, well, so this is the melt stake. Wait, before I talk about the melt stake, I wanted to say one more thing about like these autonomous boats and stuff. So for the past sort of 5-10 years, we've had these like remote controlled kayaks. And then, we decided that we would build some slightly bigger boats, which are the ones that Meagan just showed you. And, when we were trying to figure out how to control them, we didn't really know what to do. And we thought we'd use a commercial autopilot. And so we found that Garmin actually made a little autopilot for like small boats. And we were so fortunate because I don't know if you guys know, I mean, Garmin has a division here in Newport, and it was actually one of the engineers here in Newport that modified their Garmin system, and we are the only people that they're letting use. And they gave us, you know, these Garmin units with changed firmware so that we can actually control them with our little boat. So I guess I just feel really grateful that we have like such great community members here who sort of just like work with us to make these crazy things happen. So anyway, this is one of the other, Meagan showed you the lab on the ship. Our lab back in Corvallis is actually not that much more organized than this, and that's partly because I'm involved. But what we've done with that is made these crazy devices, and this is something we call a melt stake. And the whole goal here is to make a lot of measurements right up close to the ice boundary, because we want to understand the dynamics of the turbulent flow of all these chaotic motions that are bringing warm water to the ice and making it melt. And you can just see a variety of different things there. But what we did was we took commercial ice climbing screws that you use if you were an ice climber, which are those things on the left. And we tried to figure out a way to make a device, drill those into the ice so that we could attach all these instruments. There's a bunch of acoustic measurements that measure the velocity. There's cameras, there's temperature sensors and whatnot. And then Noah is the person that sort of is an engineer who works with us in back in Corvallis that helped put this together. And this is about the size of what it is. And so what we did is we built this crazy thing. We then attached it to a remotely operated vehicle, which is here. And that remotely operated vehicle, we attached to our autonomous boat. And there's Kaylin and who is that? Noah? Oh, it is Noah. Okay. So Kaylin and Noah are driving this boat autonomously to the face. And then Noah has also built a winch system that allows us to lower this ROV into the water. And then we drive it to the ice face, lower it to the water. And then we can see a little video maybe as we try to drill this thing in. So we've driven it towards the ice, and then we acoustically call to it and say, drill, and it spins those little, those rods around, and it gets stuck onto the ice. And so this is all happening a half a mile away from our boat. We're all safe, and it is in some crazy place in Alaska. We are actually in Alaska too, but we're not right there. And so now we've released from it, and now so it's stuck on the ice face. We're in our little ROV and we're looking, okay, it's stuck there. This is great. Oh yeah, and the ice is melting away. It is melting away at 1 meter a day. So every hour it's sort of going 10 centimeters away from us. And so every 20 minutes, we need to screw it in a little bit more. So it just is in this automatic thing, and it keeps moving in, moving in, moving in, moving in. These guys are measuring velocity. There's a little thing that is measuring the temperature. We're measuring the temperature boundary layer right near the ice because nobody's ever done that before. Okay, and then at the end of the mission, we ask it to come back home, and it goes, you'll see it, it will drill itself out, won't you? We'll send a little command, drill, drill, drill. So now it's spinning itself out, and then it happens to be light. Oh, that was the other thing. We wanted to have it so it would rise back to the surface so we could get it again. Comes back to the surface, and then it floats by and we pick it up. So the exciting things are, the super exciting thing is that we can measure the rate the ice is melting, and nobody's ever done that before. And that's this, oh, I was told I wasn't allowed to leave the box, but I'm going to. Can you not, don't tell Cinnamon. Oh, is there a pointer? Well, anyway, so the bottom plot here shows the distance that the ice is away from our device. And for the first 3/4 of this plot, the distance was moving away at a rate which is about 2 centimeters an hour. And then it changes slope. and it's now moving away at 5 centimeters an hour. And that happens where, if you go above that, the water had warmed up, the currents had gotten faster, and this all sort of makes sense. The water warms up, the currents move faster, and it starts to melt faster, and it moves away from us faster. So this was sort of the first time we've ever sort of seen this in the wild. So we were really excited. Not only were we excited, the seals were excited too, because this is their natural environment, and there's so many seals there, and they're partly there because it's so productive and exciting of a place, right? Right.
Right. I think other people in this room could tell us more about the seals. We were just thought they were really cute. So bringing us back to this diagram here. So Jonathan introduced this before, and we're zooming in to the face of this tidewater glacier. And now the rest of our talk is really going to focus on what's happening at this face and what we think could be the reasons why the glacier is melting faster than the models predicted to. Okay, so this is zoomed into one little section of ice. And here we have this teal buoyant plume rising up the face of the ice. The ice is white over here, and it's layered this way because those are like mimicking layers of snow that form the ice. And we think that there's 3 different, and maybe more, different mechanisms that cause the ice to melt. We're going to talk about them in reverse order. So number 3, this is increased melt drives stronger and more turbulent rising plumes. So as Jonathan was saying, we have this fresh water, and it's being melted off the ice, but it's melting into salt water. So it buoyantly rises to the surface, pulling a bunch of the salty water with it, and creates these currents that are, 20 centimeters to 2 meters per second. So it's really fast. If you think about swimming against a 2 meter per second current, I think most people, probably even like Michael Phelps people, would be struggling. 2 meters per second is really fast. Second process is morphodynamics of the face. So what does the face of the ice actually look like? We can see it above water, but what does it look like underwater, and how does the shape matter to the melt? And then the third process is the ice is full of bubbles, and Erin's going to tell us why. And we think that those bubbles could be really important for mixing heat and salt to the ice at the very small millimeter scales that are important for melt. So we have this question: how do interactions between near boundary bubble burst, ice morphology, and buoyant melt plumes accelerate melt? So process number 3, buoyant boundary flows.
Me? Okay, so we've all seen clouds in the atmosphere rising over like the hot plains of Kansas, or I don't know, thunderstorms in the Midwest or whatever, maybe even here in, do you see these things in Newport? Not sometimes, not, but so anyway, this is what we are seeing, or what we believe is going on at the glacier face. So we have rising, those clouds are rising up because they're warm. Well, they're warm, they're also moist, and moist air happens to be lighter. But anyway, that's another topic. So those buoyant plumes are like what we envision are happening at the glacier face. I just wanted to give you a little bit of an example of the types of things that, this is sort of a visualization. This is a numerical model that one of our postdocs, Ken Zhao, did, showing warm waters rising towards the surface. And this is what the models suggest is going on. And I think what we told you already was we have models that can do this, but those models seem to be predicting that the flows, the melt rates, they're all sort of a factor of 10 or 100 too small. And so the whole idea of what we're out there is to try to figure out what is wrong with these models that can't predict the melt to be as strong as we see it. And I'm just going to give you a little bit of a teaser. Erin didn't want me to show too much data, but I'm showing data anyway. What was super exciting, the panels, so time goes up on these axes, and its distance from the ice is in the x-axis. The panel on the left is the along ice velocity. The panel in the middle is the upward velocity, and the panel on the right is the temperature. And I'm not going to talk very much about this except to say, we measured these vertical rising plumes, which is the middle panel, of these red pulses. And each red pulse is another pulse of turbulent motion, those like convective cloudy things rising up the face, bringing in warm waters, which is the right panel, and taking the cold melt waters and ejecting them out. And so it's this process of drawing in warm waters, ejecting cold waters out into the ocean that we're trying to understand. And I'll leave it, I think, at that. And I won't leave it at that, because I'm going to show one more thing. Everybody laughs, but I'm showing one more thing, and that is these are sort of the first our first estimates of the observed melt versus the predicted melt with a model. On the right, on the bottom axis, it's the sort of prediction. On the y-axis, it's the observed melt. And it might look like they're sort of lying on that line, but the key is that on the down here on the lower corner here, these observed melt rates are actually, 2, 5, 10 times larger than what is predicted by the model down here. And so these are sort of our first estimate, our first understandings of what's going on. So without further ado, I'm going to pass it to Meagan. More for dynamics.
We are tag teaming this, so we will pass it around. So the next thing that we wanted to look at was how does the shape of that ice surface how does that relate to these flow dynamics? Because the flow of the water will be different on a very flat, shiny surface as compared to a very textured surface. And what we observe out there, all the models are made with these nice flat surfaces. But when we're out there looking at, like, this is an iceberg, they're full of like these big channels and small channels and scalloped, kind of scooped out pieces. And it's just incredible surface morphology. So the shape of the surface is really complex. And so the models are not capturing any of that. And that's one of the critical things that we wanted to be able to understand, because we believe that there's feedbacks not only between the turbulent water flow and where the water flows and where it gets funneled here and there and what's going on with all of those dynamics, but the ice itself, because the ice has these layered properties, it has fractures in it. So the ice itself can affect where the water is going to flow and how it's going to melt. And so we looked at this through a few different ways, and one of which is taking the big picture of, well, let's look at what the glacier looks like on this scale. So what does this complicated surface of the glacier look like? And the easiest way to do that in this day and age is to use some little drones to fly around, and we take a whole bunch of pictures, and a few of the people who helped fly these drones are in the audience. And we can fly these drones and then use structure from motion, which is a pretty automated technology now. It's pretty amazing what we can do now to take that sequence of pictures from the air and turn it into a detailed digital elevation model, which is what's shown in the right there is the elevation. So it shows you that the glacier is flowing down from high to low elevation, but you can see all of the subtleties in there. And then when you overlay the imagery with the digital elevation model, you get this really detailed 3D perspective of the glacier from above. But that's just one level of the structure that's within the ice that can influence all of this. We also want to look zoomed in at the front of the glacier. And as we zoomed in more and more, we basically just saw more and more complex patterns that are some combination of processes of the ice and of the water. And we're still trying to tease some of these out, but you can see in this middle lower section, they're a bit faint in here, but they're very faint vertical streaks. And this is at the tide line where the water goes up and down and up and down. So we can see some of the underwater processes by looking at the above water when it's above water during the tide. And I'm going to pass this off to Megan.
So we also wanted to image what the glacier looks like underwater. And you all saw some of the videos, and it's, scary. And this instrument that we need to use to image what's happening underwater costs $300,000. So, so we hired Drummond, Wengrove, and Jacob Amos at the iLab here at Hatfield to help us design a system that could protect our little multi-beam sonar baby from potential ice fields as best as it could. Of course, something could happen out of its control. And we call it the Yeti Impact Protector. And I'll tell you why on the next slide. So what it does is it's this cage here, and we can remotely tell it to lower the sonar, which is this black thing, down into its sampling position, which is what it's looking like over here on the right-hand side. And we can also tell it remotely to raise it up. So if something scary is happening, I tell Jasmine, who's driving, raise it up, raise it up, raise it up. And she does her best to click the button to raise it up. So what this thing is doing, this is what we're doing on the bridge. This is Jasmine. Jasmine is controlling the boat and the Yeti Impact Protector. This is me, and this is Nadia, and Nadia is a grad student on the project. We usually have to have some kind of candy because, like I said, it's stressful, and that helps. It's called the Yeti Impact Protector because this Yeti here just appeared on the impact protector. And so the Yeti is our little protection gnome, I guess, of sorts. And it's out there all the time with Polly, the boat, and protecting the Maybelline, the multi-beam. So we have Polly driving with Maybelline and the Yeti Impact Protector towards the glacier.
And
here.
we're all yelling at Jasmine to do things.
Yeah. And Jasmine is I think Jasmine and Cinnamon should meet each other because they're somewhat kindred spirits. Okay, so this is kind of what we get. So above the water, we have aerial reconstruction using structure for motion from the drone imagery of the glacier. So that's the color pretty part above. And then below, which it's hard to see all the structure in this particular image because it's colored by depth, but we have the data that the multi-beam is collecting underwater. And there's actually a lot that we can get from this. So if we zoom in to a certain part of the glacier, and then we take out the overall shape, like the slope, we can recover this image here, which is showing all these vertical channels that we're seeing in the ice that are like 5 meters, 2 to 5 meters in wavelength. And so it's all channeled, the whole face of the ice. So if you look at this image, the red is coming out towards you and the blue is going into the page. So we can see that the relief of some of these channels is over 4 meters. So it's pretty crazy. Nadia did a lot of this processing and has found some preliminary results showing that the glacier is actually about 60% bigger than a flat surface. And all the models are assuming that it's a flat plane. It's not a flat plane, it's a rough plane. So we think that this channelization could really impact the way the ice is melting, but also how much surface area of ice is exposed to melt.
And we can also continue to get more of this information from the drones, which give us a little bit higher resolution than the multi-beam, but they really pair well together in looking at icebergs as they come up. And so this particular iceberg is one that came up right at the end. We were all sitting there. We were all on the boat. We were all watching it, and we saw when it popped up, and within minutes we had a drone flying around, several drones, I think, flying around, trying not to crash into each other, mapping out and taking pictures of this iceberg from every direction, because it was one of the bigger ones that we saw while we were there. This iceberg is probably on the order of 50 meters from top here. Whoops. Top to bottom, maybe even more than that. There's a little bit that's gotten cut off here. And so it's 20 or 30 meters wide, and it's pretty thick into the water that we can't see. So this one was one of the bigger, Jonathan?
And it was unique that it didn't break.
Yeah, typically they will break into pieces as they come up. So it came up from the bottom of the ocean. It wasn't like a falling calving event. This comes up from the bottom of the ocean, the bottom of the glacier towards the top. And by getting the imagery and being able to create a digital elevation model of this at really high resolution using the drones, we can see these channels that are very similar to what Meagan was just talking about. But interestingly, this particular one it has some cross-cutting analogies. So all the geologists in the room might appreciate the structural geology in here, where we have big channels cutting this way. We have these little somethings going on, like a little ladder going up here that we don't understand. We have these smaller cut-in channels that are probably tens of centimeters across, and then a few kind of diagonal splaying ones. And so these are some of the questions that we're asking. We don't have all the answers on this yet, but some of the movement and flow and direction of the water coming up from deep on the glacier, that fresh water that comes out at the bottom of the glacier. Remember, it comes out basically like a river. There's a few large channels that deliver this water from the underneath the glacier out into the fjord. And then that water as a river shoots straight up into the salty water because of its buoyancy. And that process of going horizontally under the glacier and then suddenly shooting up vertically causes chaos that we don't quite understand yet. But we want to be able to use these as a way to understand the details of this ice ocean process. These are all things that pretty much nobody has measured and understood successfully yet. So we are trying to do a little bit here. But then we come to our last really detail of what complicates this ice ocean boundary. And this is the question that Meagan introduced earlier, which is the idea that glacier ice is formed from compacted snow high up in the mountains. That snow compacted, it contains air. As the snow gets compressed and turned into ice, those air pockets turn into these bubbles that are frozen in suspension in the ice matrix. And little fun fact, if you go buy a block of party ice at Fred Meyer or something, it turns out they manufacture that ice by taking shaved ice and putting it in a compressor. They don't freeze it from water. So your party ice from your party blocks of ice from Fred Meyer actually are a little bit more like glacier ice than they are like lake ice or sea ice. But anyway, this is what beautiful glacier ice normally looks like. This is from Greenland probably, which is one of the samples that we used. If you have a nice structured these are the same bubbles that we use to go back 800,000 years in knowing what our atmospheric components are back through time, and we're trying to go back farther than that. But these are the same bubbles that we use to go back in time. They have now flown. They have now flowed from the center of Antarctica or Greenland, wherever you happen to be, or high up in Alaska, all the way down to the coast. They get compressed and they turn into very pressurized little suspended bubbles that when they melt out, they sound like this. which may not be that interesting from some perspectives. It's like a babbling brook. It's a cross between like a sizzling pan in your kitchen and a babbling brook, depending on where you are. But what that is these little bubbles popping out of the ice. And here, if you look, this is a time-lapse sequence from a laboratory experiment where a little tiny bubble pops out of the ice. And that process of popping out from the ice actually explodes through the water that was there. It messes with the boundary layer water, and it also is all air, so it's super buoyant. So we have these little explosions from the ice into the water that totally add on to everything that we've just told you. And Megan's going to tell you how we know this is happening.
Yeah. So when I kind of first met Erin, we started talking about our science, what we do, and Erin's telling me about these little bubbles that explode out of the ice and they make sound. And I was like, wait, they can't only make sound. They have to mix, fluid as well, and they're disrupting this thing called the viscous sublayer, which maybe many people don't know about, but it's this very thin layer next to all surfaces in like wind or currents. And it's really important for mixing of nutrients in an estuary, or melting of ice or transporting momentum. And I was like, they have to do more. So we just did this little experiment in a fish tank. This was before we had anything funded by these foundations. And we did this technique called particle image velocimetry to look at the flow of the water right next to the ice. So this is our little setup. And what we saw were these two different boundary layers. On the left-hand side, we have clear ice. So this ice has no bubbles, and this is what all of the models are assuming. We got an ice carver in Eugene to donate this ice for us. And we look at the flow. So the flow is really slow, and it's creeping up the face of this ice. And then on the right, we have the glacier ice that's from Greenland, donated from Ed Brooks, the climate scientist at OSU. And we have all these bubbles that are popping out of the ice, and they're rising to the surface. And so in a cartoon, what we found is that the clear ice does have some the melt water does have some buoyancy. That's this blue line right next to the ice, which is on the left. Where the bubble ice, the bubbles are popping out of the ice and rising to the surface. So this red line is showing that the velocity of the flow is a lot stronger, the boundary layer is wider, and we're actually mixing a lot more momentum to the face of the ice, causing the ice to melt over 2 times faster, the glacier ice, than the clear ice. And so we're like, maybe this could be a mechanism causing the glaciers to melt faster in the field too. Well, we haven't gotten there yet. That's up next for us. But if we come back to our cartoon here, we said we had 3 processes. The convection of the turbulent rise of the water next to the face of the ice. We're measuring that with the melt stake, and we're finding already a lot of things about the temperature structure and the velocity structure that are different than what we knew before. We found that the ice is not flat, basically. There's lots of channels and crazy features that we're learning could be really important for how the ice is melting. And then also these bubbles are this little tiny process that could be so important for ice melt. And in the lab, it makes the ice melt over 2 times faster than clear ice. So with that, we have field plans this summer, and we're driving the robotic boats to the face of the glacier. And we are looking to avoid, these big events. But excited for the findings that we'll have in the 2 field campaigns coming up. So of course there's three. So that's a little. But
Go.
I was like, Jasmine, 180. Yeah. Faster, faster. She's like, I'm going faster.
No. And then I'm like, no, turn around. There's good data to be had.
Yeah. Okay. So of course it's not only the three of us standing up here. There's a whole team of excited students and engineers and lots of opportunities to be had. We're looking forward to this summer being another fun time. Everyone gets along pretty well, even in these really tight quarters. But we have like the Lucys up there, and they might be able to tell you some other stories. So thank you for talking or letting us chat with you. And here's a list of lots of people on our team.
That was so cool. Okay. So we're going to start opening up to questions. We're going to bounce back and forth between folks online and folks in the room. And I know that Roseanne has questions, so we're going to start there. Go ahead, Roseanne.
How variable is the melt with the depth of the glacier in the water? And does the amount of air in the ice vary with the thickness? This was a very fun presentation.
I can start, and then Erin can continue. So with the bubbles, we know that there is distribution. Some pieces of ice are really clear and don't have bubbles at all, and other pieces of ice have tons of bubbles. We also know that as you go deeper, the bubbles actually have pressures of measured in the field of up to 20 atmospheres. So that's a lot, right? That's a lot of pressure. But the glacier is 200 meters deep. And so at the bottom of the glacier, those bubbles have less pressure than the water pressure. So they're not exploding out as much. The bubbles, we think, have the biggest influence within 60 meters of the surface. So 60 meters and shallower, they have a pretty big influence dependent upon their pressure. We also have seen, I guess, from the past that there's do you want to talk about the intrusions? The meltwater intrusions coming off the face of the ice, and so these are as the fresh and the salt water mixes together, the density of the water equilibrates, becomes the same as the seawater at some elevations. So you have these like plumes of cold water coming off the face of the glacier, and we think that there is some dependence upon the distribution of these meltwater intrusions and how much ice is melting. And that's something we still kind of have to figure out.
Yeah, and just to add, I mean, that was a really good question. I don't think we know a lot of those answers. So yeah.
All right, questions in the room.
That beginning slide that you had with the glacier in Antarctica, and you said from, I think it was April to, was it August? It was losing 20 meters a day. I think that's
the glacier in Alaska.
Was it Alaska?
The Alaska one loses 20 meters a day most year round. It speeds up a little bit in the summertime and slows down a little bit in the winter, but it's moving 20 meters a day.
But it never builds itself up.
Sorry?
It never builds itself up again or any.
It's being built up continuously by snowfall way up on the Stikine ice field. So this particular glacier is being fed by snowfall in the Stikine ice field high up. And then this glacier is one of the main pathways that the ice from the Stikine ice field makes its way to the ocean. So as long as the upstream snowfall can provide enough of a source for that, it will continue to put out 20 meters a day. If the Stikine ice field can't provide it all, then that glacier will retreat upstream until it reaches a balance between that source snowfall and what it loses into the ocean.
And this particular picture goes from April through August, and you can see it's flowing in, but it's gradually retreating as time goes by. And then the next year it will reset. Some years it'll be further out and some years it'll be further back. but
All right, questions online. Go ahead, Roseanne.
All three of those melt enhancing effects look like positive feedback processes, each of them both enhancing itself as well as enhancing the others. Is there any way to measure this feedback and see how much it might contribute to your 10 to 100 times difference?
like, that's the best question ever. You know, I mean, that's exactly what we're trying to do. And does anybody have a good answer to how we're doing it? I mean, what we're doing is we're trying to measure the individual components by themselves. We're trying to model the individual parts by themselves. And then we're trying to put the whole thing together to see how, if you increase this effect and you increase that, and it does this to that, and it does that to this, then you get that.
Yeah, and we also are doing like some laboratory experiments, like we showed with the bubbles, which can help us isolate a process and then try to combine them all. But it's a great question. All the feedbacks, it's really hard and complicated problem to realize. Yeah.
All right, questions in the room. Okay, hang on, everybody. My grad students like to make me run. Thanks for a really interesting and great talk. It sounds like a lot of the results and field work that you described is from this glacier in Alaska, and I'm wondering how much can you generalize what you're learning from this glacier to glaciers around the world? I would imagine that especially processes like 2 and 3 could be pretty unique to each glacier.
Yeah, I'll start with that from the glacier side, and that's that while there is uniqueness to especially process 3 and then some of the structural pieces like the fracture properties of the glacier, while yes, they are different at every glacier, one of the things we are doing is doing a bit of an assessment based on all the theory that's been developed over the last 70 years of glaciology to try to put some quantitative value on, well, what do we expect in these regards at an Alaskan glacier that is warmer and maybe has a lot more flow complexity versus in Antarctica, where I actually do expect the bubbles to generally be more uniform and there to be less of the like overfolding complicated flow patterns. So if you showed me a glacier, I would look upstream, and knowing what I know about how glaciers work and the environment that glacier has flowed in, I can start to put some bounds on that. So it's not that every glacier is totally different. We can definitely put some bounds on what to expect from each glacier environment. And I think the same is true on the ocean side, where the temperature and the types of currents that are available to the outside of the fjord do vary, but if they vary in a way that we can put some bounds on what we'd expect in a particular fjord, we expect, certain temperatures of water and certain times, certain effects of the tides or certain things going on, we can extend this work. And we do want to do some work in Greenland to kind of make sure that what we're thinking in terms of the extension of this work actually makes sense.
All right, question online, Roseanne.
Any idea how old the ice in the glacier is by the time it reaches the ocean?
Well, that's a little bit of a philosophical question. And that is different for every glacier. So when the snow falls up high, you have some of the snow falls and then it doesn't go very deep in the glacier and it comes back out. Some of it falls up higher and it goes way down deep and then it comes out. And we can do the same thing, like look at a glacier and go upstream and use some estimates of how much it's flowing, how deep the glacier is, using all of the characteristics of a glacier to figure that out. And for something like the Zick Glacier that comes off the Stickeen ice field, I would guess it's on the order of a couple hundred years to maybe 1,000 years for the deepest glacier ice. The ice that we used for the Greenland work came from the southwestern margin of the ice sheet, I think. And for the bubble experiment, and that was I think on the order of 10,000 years. I forget exactly which depth that one came from. But we do have ways to estimate that. And there, like I said, the ice, some of the oldest ice in Antarctica right now that has been dated is 850,000 years, but we actually just dated a sample. This is a program also at the Corvallis campus called Coldex, where we're part of a big collaboration that has just dated a 6 million year old piece of ice from Antarctica. That one is not melting out into the ocean right now. Fortunately, otherwise we would be very quickly trying to measure it. Hopefully that.
All right. I recognize that we are at time. So, all right, hang in there, everybody. I'm going to go all the way to the top. Do you want to meet me partway down? No. You have a question? Maybe mom can help.
Liana wants to know how they named things.
How did you come up with your cool names?
Yeah, so I can speak for a couple of them. The Yeti Impact Protector, because we ended up with a Yeti. Oh, a Yeti on the front of it protecting. So that was that one. Maybelline the multi-beam just sounded cool.
I mean, Poly is Poly because the boat is made by Polaris, and so there's Poly and Aries.
Perfect.
And then we have Dragon that we didn't talk about today. And Dragon is just because we drag it up and down, and we just like the name Dragon. And Melt Steak, this one is just Melt Steak because it measures melt.
And then we had another ROV that we didn't show, and her name was Dolly, after Dolly Parton, because Nadia, who is a grad student on the project, wanted to name it after, who is from North Carolina, wanted to name it after a strong Southern woman.
Perfect. So, again, I just want to give a round of applause for our presenters, please. So for folks online, if you have any remaining questions, hang on. I'll have our presenters kind of answer some of those questions. For folks in the room, you can also come up and speak to our presenters for a little bit longer. I also will just put a plug. Everybody up here will be at Marine Science Day. So if you want to come and talk to them, come visit them then. For everybody, keep watching. Our next Science on Tap will be next month, and I hope to see you again. Thank you, everybody. For folks online, we're going to end the presentation. We'll see you next time.